Yesterday we learned about two types of curved mirrors, concave and convex. Another name for concave was converging. We call it a concave mirror sometimes because it's caved in the middle. It's thinner in the middle than it is at the edges. If this is what we call our principal axis, that imaginary line drawn at 90 degrees to the mirror and right through the middle of the mirror, then this would be a curved concave mirror. It's thinner in the middle than it is at the edges. It's caved in. We also call it converging. Why? Caved in gives you concave, but where does converging come from? Rays that are coming at this mirror converge. They come together. In fact, rays that are parallel to the principal axis will all converge at the same place. What do we call that place that they all converge? The focal point. Now, there's a point out here that's twice the distance of the focal length. If that's f, then this is going to be 2f. What do we call that? Somebody said it? Yeah, it's the center of curvature. It also corresponds to the radius of the circle. So if we completed the circle for this mirror, then 2f would correspond to the radius. In other words, the focal length would be half the radius of the circle. All right, let's look at the other kind of mirror. We have a diverging or convex mirror. This is called a convex mirror because it's bulged out. It's convex or bulged out in the middle. It's thicker in the middle than it is at the edges. Why do we call it a diverging mirror? Rays of light that are parallel to the principal axis don't converge anywhere. Rather, they diverge. They spread out. They spread out away from the focal point. So the focal point's on the other side of the mirror this time. It's called a virtual focal point because rays of light don't really converge there. They never make it there. The rays of light hit the mirror and then they reflect off of it as if they were coming from the focal point. Now we'd say 2f is over here, or the center of curvature is over here as well. All rays parallel to the principal axis diverge or spread out away from the focal point. All right. Let's take a look at a few of the ray diagrams that we drew yesterday here. Let's draw 3 of these ones. First ray is going to go from the top of this object down through the focal point. Always. That's the first ray we'll always draw. The second ray is going to go from the top of this object down through the focal point, and it's going to reflect parallel to the principal axis. Symmetry of physics again. Parallel through the focal point, parallel. Where's our image formed? Well, if our object was right here, this is you, by the way. If you're looking into the mirror, this black arrow is you. This is the object. Okay, it's whatever is sitting physically sitting in front of the mirror or standing in front of the mirror. The arrow represents the top of the object. Well, if that's the object, then the image is going to be over here. The object starts at the principal axis, so does the image start at the principal axis. The object ends where the rays of light start. The image ends where the rays of light converge. That means that this image is going to be, if you look at the characteristics or the attributes of it, it's going to be upside down. It's going to be larger. If you look at the size of this image, this red image, what you see when you look in the mirror versus the size of you, the object, I think it's pretty clear that the image is bigger than the object. What you see is bigger than what's reality. And the third thing, is it real or virtual? This one's real. How do you know it's real? Somebody said it. Solid lines intersect here. Solid lines come together. This is real, which means we could, if we wanted to, project it onto a screen. Not that we have to, but we could if we wanted to. You go to a movie theater, the image is being projected onto a screen. That's a real image, right? If we took the screen away and they kept projecting the movie, then you wouldn't see it by looking down there at where the screen was, but you could turn around and look into the projector to see it. We'd still call it a real image, even if it's not being projected onto the screen at the time, because it could be if we wanted to. Okay, this is a real image because we could, if we wanted to, project it onto a screen. But what about this one? What happens when our object is at F? It's right at the focal length. First ray, parallel, down through the focal point. Second ray, this one's different. This one's going from the top of the object away from the focal point. And then it reflects back, sorry, not the focal point, but the center of curvature. And then it reflects back straight through the center of curvature. Do those rays intersect? So let's extend them to see if they intersect now. Extend the reflected ray, not this one, but this one. Do they intersect on that side? No, there's no image. You bring that concave spoon far away from you, bring it closer. It starts off upside down and bigger. Sorry, upside down and smaller. And then it gets upside down and bigger as you bring it closer to you. And then it disappears. There is no image formed when you've reached the focal point of that mirror. One more for this kind of mirror, that is. Here's our object really close to the mirror. First ray, parallel to the focal point. Second ray, away from the center of curvature, and then back through the center of curvature. They don't intersect. Extend the reflected rays. They're going to intersect over here now. What do you know about this one? It's bigger. The image is bigger than the object. It's upright. And it's virtual. No matter what you do, you can't project this onto a screen. It's physically impossible. You can see it by looking at the mirror, but you can't project it. What you see right here in this diagram is the picture of this guy looking in the mirror right here. Look at how close he is. He's inside the focal length. What are the characteristics that he's going to see? Connor? He's going to see an image that's virtual. Hey, he's looking into the mirror. It's okay. You can see it. Look into the mirror. It's going to be right side up, and it's going to be bigger. If he was to back up, what would he see? He's standing right there in front of that mirror. He backs up. What does he see? At some point, pretty soon, he'd see nothing. And then he backs up a little bit more, and he'd see an image that is bigger and upside down. And then as he keeps backing up, it would remain upside down, but eventually it would end up getting smaller than the object is. Eventually, the image would end up being so small that he wouldn't see it. But having said that, Ethan, even when he's too far away from the mirror to see it, we'd still say that there's an image formed on that mirror. It would just be so small that you couldn't see it. That's all. All right, let's take a look at the ray diagrams that we drew for the other kind of mirror, the convex or diverging mirror. This one right here. Didn't matter where we drew our object, we get the same characteristics here. First one, wherever it is, okay? Put it anywhere, it doesn't matter. The first ray is going to go parallel to the principal axis. Where does it go from there? It doesn't converge anywhere. It diverges away from the focal point. So it's as if it wants to go down there to the focal point, but it doesn't. It reflects off of the mirror and goes up this way. The second ray wants to go straight to the focal point, but it doesn't because the mirror gets in the way and it has to reflect. So it reflects parallel to the principal axis. Parallel away from the focal point, then go toward the focal point, it reflects parallel. They don't intersect, so let's extend them. The reflected portion of the wave gets extended back here. The reflected portion of this wave gets extended back here, and they converge. Where? Well, they converge somewhere on the other side of the mirror, which means that it is a virtual image. Dotted lines intersect. We could not project it onto a screen. It's smaller, clearly, than the object, and it's upright. That's the convenience store mirror that we saw right here. You look into this, and what do you see? You see an image. that's smaller. It's smaller than the object. It's upright, and we can't tell by looking at it, but ultimately we know it's a virtual image. We couldn't project that onto the screen even if we tried. You guys drew the 5 ray diagrams, or you're supposed to at least draw the 5 ray diagrams for these convex mirrors. Oh, that's right, yeah. When you do that, you find that the images, they may shift in location a little bit. They may shift in size a little bit, but the characteristics of all 5 of those images will be the same. They will always be smaller, they'll always be upright, and they'll always be virtual. Where have you seen one of these convex mirrors before? Besides, we mentioned yesterday, I think, at the swimming pool in Okotoks. Where else have you seen one?
There's a road with like a wall right on the curve. You're into the curve and you can't see around.
Oh yeah, okay, yeah. Yeah, you know what? I remember where there's one of those actually. If you go down where the ATB branch is, in front of Centennial, like the Centennial Center. When you're going in there by kind of behind Shoppers Drug Mart, in between the gas station, between the co-op gas station and the ATB branch there, you drive in that little road, and like the building literally comes right to the corner, so you can't see around it. So there's one of those convex mirrors there. It helps you to see around it, right? Now the upside is, or the downside is that the image is pretty small, right? But the upside is because it's so small, you can actually see a pretty wide range, pretty big field of view in there, right? Okay, good. Where else have you seen one? How many people drive? Most of you drive, right? You got to pass somebody, and you got to pull in to pass, and you're supposed to shoulder check, right? When I was your age, I drove a delivery van for a dry cleaner. There was no windows in the back of the van. There were no windows because it was a cargo van. So I had to learn to use my mirrors. When I was 16, I had to learn to use my mirrors to back up and to pull in and pass and whatever. Well, when you pull in to pass and you use your mirrors, you realize, oh wait, it says something on the mirror. What does it say? Objects in mirror are closer than they appear. Why? Why is that the case? Well, because it's the image formed in the mirror is smaller. And why is it smaller? Well, we want it to be smaller so that we can see a wider range. Try pulling in to pass when you're passing somebody if the image that you see in that mirror is life size. All you're going to see is part of a car behind you, right? It doesn't work very well. You need to see a wider range like you do when you're going around the ATB branch in Okotoks, right? You need to see a wider range. So how do they do that? They make it slightly convex. If you look at that mirror, it's slightly bulged out in the middle. That makes it convex, which means that the image is going to be virtual, upright, and smaller, but it's going to allow you to see a little bit bigger field of view. Right? Where else have you seen it? This one might bother you, actually. Some of you, at least. You know that you don't actually have to have a double convex lens, sorry, double convex mirror, a convex on both axes. It can be convex on one axis, right? If it's a sphere, if it's like a basketball, kind of the end of a basketball sliced off, then it's convex on both axes, X and Y. But you can get a mirror that's convex on only the X axis like this, or only the Y axis like this, right? And we can go through that analysis as well. If it's convex like a basketball is, then the image characteristics are that it is smaller, it's upright and virtual on both axes. So in other words, it's proportional. You look smaller, but you look smaller on both X and Y axis. So your proportions still stay the same, right? But if you happen to go into a change room sometime, and you happen to look into the mirror and think, boy, I look really good. I look really thin in that outfit. Maybe it's because there's a slightly convex mirror, convex on the x-axis. What happens then? Well, on the y-axis, you remain the same height, right? You don't shrink on the y-axis because it's flat on the y-axis. But on the x-axis, what are the characteristics of the image on the x-axis? Virtual, that's fine. Upright, that's fine. And smaller. So you appear same size vertically, but smaller horizontally. Then you get home and you're like, wait a second, I thought I looked better in this. I thought I looked thinner in this. Yeah, some of them would. So you should, yeah, yeah. I think it would be more likely to see that in a women's change room than a men's change room. But all right, if we draw our array diagrams, we can predict what our image is going to look like. Real or virtual, bigger or smaller, upright or upside down. But we can predict more accurately by using mathematics. There's two equations that we can use to describe the images formed by curved mirrors. The first one we call the mirror equation. It's 1 over f is equal to 1 over dO plus 1 over di. What do you think f stands for? No. In this context, it doesn't stand for frequency at all. You got to be careful because yesterday, in fact, earlier today, when we were checking over homework for the Michelson experiment, f stood for frequency. Now it doesn't. F stands for the focal length. And the focal length is the distance from the mirror to the focal point. It's half the radius, half the distance to the center of curvature. dO, 1 over dO plus 1 over di, yeah. We'll deal with that. dO stands for the object distance. The object distance is the distance from the mirror to wherever the object is. It's always, everything we got here is measured from the mirror. dO, di, f, always measured from the mirror. dO is the distance from the object to the mirror. And di, of course, is the image distance. And that's the distance from the image to the mirror. Now, what about the units here? What units should we use here? Well, the standard units are meters, right? But if you put meters in every term, then they would actually cancel out. That means that it doesn't really matter what units we use. Meters, centimeters, inches, kilometers, miles, it doesn't matter. The standard units are meters and they work just fine, but centimeters are probably the more common units that we use here. You don't have to use centimeters. If you're not comfortable with that because you're used to using the standard units, then use the standard, use meters. Always convert, it'll always work for you. But centimeters works here as well, as does any other unit, as long as you're consistent. Doesn't matter as long as you're consistent. Now, the other equation that describes this, called our magnification equation, M, which stands for the magnification. And magnification, I gotta learn to spell this. The magnification of the image is how big the image is relative to the size of the object. So if the object is 2 centimeters high and the image is 6 centimeters high, then the magnification would be 3. In biology class, you use microscopes where the magnification of the ocular lens, I think, is 4. And the magnification of the objective lens would be, I think you can get, there's options, right? 10 is one of them, I think, and 100 is another one. I can't remember what the third one is. I think it's, I don't remember. It doesn't matter. Bottom line is, if you have a magnification of 10, that means the image is 10 times the size of the object. If you actually have 2 lenses, like you do in a microscope, one has a 40 times magnification, one has a 10 times magnification, then the magnification ends up being 10 times 40 or 400. It means the image would be 400 times the size of the object. And that's why you can see little things in cells, because they're 400 times bigger than they would be if you were just looking at them with the naked eye. Magnification is how big the image is compared to the size of the object. There are no units. It's just a number. Sometimes you see an X after it, but there's no units. And why are there no units? Well, if you look at the equation, the units end up canceling. What do you think HI stands for? High over Ho. HI stands for the, height of the image. And we can use whatever units we want as long as we're consistent through the question. Usually it's going to be centimeters, but it could be anything you want as long as you're consistent. But that's also equal to negative, and it's important to put this negative in here, negative di over do. Yeah, we're going to see in a minute some sign conventions. We have to make these values of hi and ho and do and di negative or positive, depending upon some characteristics of those objects and images. And if we don't put that negative in front of the di and do, then the sign conventions fall apart. Doesn't work out. We have to stick that in there arbitrarily to make the sign conventions that we use work. By the way, di and do, usually centimeters, sometimes meters or kilometers or whatever, but usually centimeters. All right, let's take a look at when they should be positive and when they should be negative. Let's look at three variables first. Let's look at f, do, and di. When's f going to be positive? When we have a real focal point. And it's going to be negative when we have a virtual focal point. But when do we have a real focal point? You go back to your ray diagrams. When did rays really go through the focal point? When we had a converging mirror. Anytime you have a converging mirror, you have a real focal point or a positive value of f. If it's a diverging mirror, then you have a negative focal point, negative focal length. Rays come together at the focal point, positive. They don't, they diverge away from that, then it's going to be negative. Do is positive if you have a real object. And it's negative if you have a virtual object. Now that seems tricky. When are we going to have a real object? Well, that doesn't seem so tricky. The virtual object is a tricky one. When do you have a real object? Well, for us in Physics 30, the good news is always. If you take a course in physics next year when you're at university, you may have a virtual object. But that's going to happen if you have a system of lenses or mirrors. Here's a mirror, here's another mirror. The image from the first mirror becomes the object of the second mirror. And in some cases, that can be a virtual object. We're not going to see that. So for us, the object is always real and therefore always positive. And the object is never virtual or never negative. Di, it's positive if the image is real. And it's negative if the image is virtual. Now, I don't expect you to have your ray diagrams memorized because we just drew them yesterday and today. But you might remember a little bit about them. You do them, use them, see them enough times, and you'll remember more about them. There were 10 ray diagrams that we drew for mirrors. One of them produced no image. 3 of them produced real images. And 6 of them produced virtual images. So 3 out of 10 times, DI will be positive, and 6 out of 10 times, DI will be negative. I don't want you to guess, but if you have to guess, what should you guess? You should guess that it's virtual. DI is negative, because you're twice as likely to be correct if you're guessing DI is negative, right? You've still got a 33% chance of being wrong, but at least you got a 66% chance of being correct. You're not sure whether it's real or virtual, draw the picture, draw the ray diagram and see whether it's real or virtual. And then decide whether to make it positive or negative. All right, what about HO and HI? Using a different color here because the convention is a little bit different for these. HO is positive, not if the object is real. DO is positive if the object is real. HO is positive if the object is If the object is right side up, then the object height is a positive value. If it's inverted, then we make it a negative value. HI is positive if the image is upright. And it's negative if the image is inverted. So you're talking about F, DO, and DI. In other words, if you're talking about anything in this first equation here, then the sign convention is based on real or virtual. If you're talking about HI or HO, then the sign convention is based on whether it's right side up or upside down. And finally, we're missing one, but it doesn't really fit in the table so well. M, magnification, is positive if the object and the image are on the same side of the principal axis. In other words, if they're both upright, M is positive. If they're both upside down, M is positive. If one of them's right side up and one of them's upside down, then M is negative. Let's take a look at one example on page 664, please. It says an object is located 20 centimeters from a converging mirror. I'm going to circle this, converging mirror. Sometimes we see a diverging mirror. In fact, by this time next week, you'll see converging mirrors, converging lenses, diverging lenses. You got to know what you're dealing with so that you know what the sign conventions are here. It's a converging mirror. If it's a converging mirror, then that means the focal length is positive. In fact, it tells us it has a focal length of 15 centimeters. That's a positive value. It would be more important to circle it if it was a diverging mirror, because F would be negative then. But we want to get in the habit of it, whether it's positive or negative, just so that when it becomes negative, it's really important to put it down. We don't forget to do it. Where will the image form relative to the mirror vertex? Or in other words, what's DI going to be? And if the object is 5 centimeters high, what's the attitude? Attitude means right side up, upside down. The height and the magnification of the image. There's a lot to this. Let's write down some givens here, okay? Let's say DO is 20 centimeters. Let's say F is positive 15.0 centimeters. We want to find DI. We have HO, and we want to find the attitude. That's not a number, right? So we'll worry about that later on. The image height, and we want to find the magnification. Look at that. We got 3 variables. We have 3 unknowns. You can deal with that. Let's write down our first equation. 1 over F is equal to 1 over DO plus 1 over DI. Look, the good news is there's only 2 equations. If you can't figure out what to do, well, try one of them. If it doesn't work, try the other one. Something's got to work for you. Oh, the mathematics comes a little tricky here, though, doesn't it? 1 over F, 1 over 15 equals 1 over 20 plus 1 over DI. You guys know how to solve for DI there? I'm going to show you a little trick on your calculator to do this really, really quickly and really efficiently. Everybody take out your calculator now, please. In order to find DI here, we need to take 1 over 20 over the other side by subtracting, right? But there's a nice quick way of doing it on your calculator. Watch carefully, and everybody follow along and do this yourself on your calculators. I want you to go 15 x to the minus 1. That's 1 over 15. Subtract 20 x to the minus 1. Press equals, and that gives me 0.01667. That doesn't give me DI, right? That gives me 1 over DI. Now, After you've pressed equals, I want you to press x to the minus 1 again. And you're going to get 60. So again, we said 15x to the minus 1 subtract 20x to the minus 1 because we had to subtract 1 over 20 from 1 over 15. It gives us 0.01667 on the left-hand side, and then we got to flip that over to get di, and end up getting 60 centimeters. Got that? All right, so there's di. Now we want to find either m or hi or something. Let's get m now. M is equal to hi over ho, but it's also negative di over do. Negative di, negative 60 divided by do is 20. So we're going to say m is equal to negative 3.00. No units. We can find hi by saying m is equal to hi over ho. And therefore hi is equal to m times ho. Negative 3, we just found that, times 5 gives me negative 15.0 centimeters. We could have said hi over ho equal to negative di over do, right? But we had to find magnification, so I thought we might as well do that first. What about the attitude of this? Right side up or upside down? We know that it's upside down, Matt. Why? Because what's negative? What distance? Because hi is negative. If hi is negative, then the image is inverted. Got it? If hi is negative, then the image is inverted. Let's go back to our table. If hi is negative, then the image is inverted. Now, di is positive. What does that mean? It doesn't say anything about the attitude or the orientation of the image. It just says that it's a real image. You can project it onto a screen. The attitude is that it's inverted. And the height is negative 15, and the magnification is neg 3. Good? You're going to look at a few questions here now. And when you're answering those questions, I want you to keep that chart off to the side so that you can see it. Don't try right now so much to go from memory on this, because you're not going to remember it. You got to have this on a piece of paper beside you as you're solving the problems. Come quiz day or test it, you got to have it remembered. But the more you use it, the more likely you are to remember it. You've never used it yet. Have it beside you. Look at it. Determine whether something should be positive or negative based on this on the table. Then do your thing. You will make lots of mistakes, a lot of mistakes, if you don't have the table beside you. Yeah, you learn by making mistakes, but it's nice to get some of them right too. And you're not going to get very many of them right if you don't have the table beside you. All right. Let's take a look at the practice problems on page 664. Questions 1, 2, 3, 4, and 5. Questions are on page 664. You can start those now.